Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I am going to explain a new paper called Almost Unsupervised Text to Speech and Automatic Speech Recognition by these authors mentioned here, and this paper was got accepted in ICML 2019, and the paper does not mention which university this paper is coming from, and I don't know which university this paper is from, but these are the authors. The paper mentions only the authors but not university or which company, and that's okay. And for the tutorial I'm going to cover first the overview of this paper, and we'll see what is the proposed method for this unsupervised text to speech and automatic speech recognition, and we'll see some experiment and we'll see the experimental setup, and finally we'll see some results also. And the paper sounds very interesting because today's speech recognition or text to speech are very difficult if you want to do them, or if you want to build these TTS models or ASR models using unsupervised data. It's a bit hard. I mean, they are like, people are trying, but we are still nowhere near reaching the state of the art, which is supervised methods. There is some effort which is being done in this space, like there is a challenge called Zero Speech Challenge. So a lot of things are going on, and we'll see this is also one of the effort to build unsupervised speech recognition and text to speech engines using unsupervised data, which is very good, because today's models need a lot of supervised data, which is very hard for collecting. And so the overview of this tutorial is like this. So first, I mean, the paper itself says it's they are building something which is almost unsupervised. When I say almost unsupervised, they are doing something sort of supervised along with unsupervised. So when they say almost unsupervised, they may be, I mean, by the words it says, maybe they are using very less amount of supervised data, but very large amount of unsupervised data, which is good. That's okay, because we can afford a very very less amount of supervised data. And so what they are saying is, for this task of ASR and TTS and ASR, they are using very few amount of paired speech text data, which is like you have audio and what is given in the audio, the text sequence, right? So they have these sort of few set of these paired sequences, and remaining is all unpaired, which is random audio data, just random audio clips, let's say, and I have random text clips, I mean text data. I mean, use this to build the model. So that's unpaired text data. And what they are trying to do is they are sort of using something called self-supervised learning for this unpaired speech to text data. We'll see what they are doing exactly. I mean, this is sort of some ideas borrowed from something called backtracking algorithms in NMT, neural machine translation. It looks similar, but we'll see how this is applied here. So the self-supervised learning is a method which is used here for learning representations from unpaired speech text data. And I mean, the same algorithms for the same model will also feed supervised data. We'll see how that is. And to understand the I mean, just since these models are unsupervised, the models needs to understand the language information, which is language understanding, and also it has to understand the speech information, which is speech representation. So that can be done using denoising auto-encoder, because denoising auto-encoder does not need any supervised data, right? So that's very easy. So we'll see this, how these are also these models are also used to leverage this new algorithm. We'll see all those things in detail. Just assume you have a denoising autoencoder, then we'll use something called dual transformations, which is where the self-supervised learning comes. We'll see what is that also, which is basically dual transformation is sort of like you use a speech recognition and you feed some audio to it, it gives you text, and use that text to generate audio using text to speech engine, and you keep doing that iteratively. I mean, it sounds like it might not converge because you are not providing any supervised signal over there. I mean, it may not work, but we'll see how that is going to work here. We'll see what are the modifications they have done to make it work. And they use something called bidirectional sequence modeling to avoid this propagation of errors. As I said, let's say you have a speech recognition model which is not working, which is like a base started like just first epoch model, which does not learn, which haven't learned anything. If you feed audio to it, it provides some junk text, And if you feed the same junk text to a text to speech engine, it gives you some junk audio, and if you feed that back to the speech recognition, I mean, it's sort of error within the loop. I mean, inside a loop, it keeps propagating. It does not make sense. We'll see how that is handled using this bidirectional sequence modeling algorithm. That's one point, an interesting thing. And they are achieving something like 99.84% intelligent word intelligible rate, which is like almost near to human. And actually, if you go to the paper and see, they have given some link where you can go and listen to the audio. I would encourage you to go and listen to those audio. And they have also calculated the mass score from text to speech, which is 2.68, which is fairly decent. I mean, it's not that bad. It's still good. And PER is 11% for the speech recognition model. It sounds very interesting. They have very good results. We'll see how these things works. So in the coming section, we'll explain this model. We'll first we'll divide this section into 4 different blocks. We'll first understand what is this denoising autoencoder. I mean, a lot of people know about this denoising autoencoder because it's a very old algorithm. And dual transformation, we'll see what is dual transformation for this TTS and ASR. And we'll see this bidirectional sequence modeling, and finally we'll see the final architecture which is used for training this model. So coming to denoising autoencoder, I mean, as everybody know, denoising autoencoder, just take example of speech. You can do the same thing for text also. We'll see how that is done for text. So let's say you have a speech data and you want to build a denoising autoencoder for it. You just take the text data, sorry, speech data, feed it through some noise layer, which is basically adding Gaussian noise to this particular spectrogram. Then you feed it to encoder. This is encoder, and you have a decoder, and the decoder will try to generate or reconstruct the original. This is the original speech, right? Let's say this is some audio clip, and if you feed this to spectrogram generator, it gives you this spectrum. Then you add noise to it, and you try to generate this. And how do you do it? You just use mean square error loss like this, and you can if you optimize this model, you'll be able to generate same spectrogram of whatever you are giving here. The model will try to generate here. And as you know, like let's say LS is the loss for the speech autoencoder, speech denoising autoencoder, which basically tries to generate X, which is the clean X from the corrupted X, which is basically C of X is basically corrupted version of X, and you try to generate X from this corrupted transaction, and in the meanwhile you also learn the encoder and decoder parameters, which is the theta encoder S stands for speech autoencoders model. And the same thing you can do it for text also. So in the text, what you want to do is you have a clean text, and let's say you corrupt the text using this C of Y function, and you try to generate that sequence Y, which is the clean text sequence from the corrected text sequence. Meanwhile, doing that, you optimize the model so that it learns the parameters for your text denoising autoencoder. And as I said, for speech you use mean square error loss, and for the text you have to use log likelihood, which is basically why this summation is because you are taking log. Basically, if I say I want to know what is the probability of X, and X could be like sequence of word X1, X2, X3 and so on, and you can model this as pre of X1 into pre of X2 given X1 and so on. You can do it, and these are multiplication, and if you apply log to it, it becomes summation, and you want to maximize this likelihood, and you want to maximize it, and if you put negativity, you will just minimize this, because I want to minimize the loss, I don't want to maximize the probability, right? It's as simple as that, very simple. So that is how the denoising autoencoder works. Now let's go to the dual transformation. Sorry about this mistake, there should be N here. Dual transformation. So basically, what is this dual transformation? Basically, as I said, let's say you have a speech recognition model here, ASR, let's call it as ASR, right? And let's say you have another model, which is text to speech model, TTS model. So let's say these models are encoder decoder model. What I do is, I'll just take one random audio file, feed it to ASR. It gives me something called Y cap. Y cap is basically, or Y hat is basically the sequence of words, let's say it is word sequence of words generated by this model, but it is not trained yet. You have to train it. Let's say this is not trained, you first feed something and it gives some chunk. Now you take this and feed it to text to speech, because text to speech engine takes text and generates audio, right. So this is how you do it. So so this is called x cap, let's say, right, and this is y cap. Now you use this x cap back here to train to feed it to ASR and try to generate y here. Same thing. So this is sort of in loop, right? This keeps doing it. The people keeps doing this, and they want to train the model using this thing, right? I mean, it's not completely like this. You can just go through here. It's like you first construct the pair of y cap x, which is basically generated text given the audio, and for this is for text to speech, and for ASR you will get the same, like you have x and you can generate y, and that goes as input to TTS, as I said. And if you keep doing that, then what happens is the loss could be like this. Loss will become like, let's say you have the same autoencoder model, and in that you will get x. Let's say you take the same model, but instead of predicting you are predicting spectrogram, right? Let's say you are predicting the audio given some text which is generated by text to speech engine, right? This is a y cap. This is one loss, and another loss is you want to generate y, which is the text sequence given the spectrogram which is generated by the speech engine or ASR engine. So this is generated by the text to speech engine, right? So you want to predict y given the audio, which is ASR. This is ASR model loss, and this is text to speech engine model loss, right? And you add these two, and you just optimize this. Once you optimize this, or once you train this model, you can actually predict your this y cap. What is this y cap? You can just ask. I mean, it's nothing but this argmax of y given x, and x cap is again the same thing. And that's how this model works. This is called a dual transformation. So as I said, it's a two model, like one's output is going to another, and another's output is going back to the other model, and this is how the training happens. And is this correct? I mean, people can say, okay, is it going to work or not? This will work, but there is one problem. The problem is, since these are sequence modeling algorithms, what happens is you don't have ground truth to train it. So what happens is, let's say you have a text to speech engine, which is a sequence model, let's say, right, which actually takes text here and tries to predict let's say sequence of spectrograms, like sequence of spectrum like this lines, right? So what happens is, these are conditional predictions. Like if I want to predict this, I want to put conditions on the previous ones, and if I'm predicting something here, I want to put conditions on all the previous ones. But what happens is, if something is wrong here, this error will get propagated, and all the parts in this region will get corrupted, and only this part is right. This is the problem. It's the same thing happens with audio also. Let's say you feed audio and you want to predict text sequence of words, and if you predict, let's say, few words correctly, and if you predict some word wrong, and all the other words will be dependent on this wrong word, and this will become wrong again, this will become wrong, and all others will get corrupted. So what usually happens is, the left part will have some good information or good sentences or good predictions. Right part will get corrupted because of the wrong predictions. So this is the problem. So for this, people have proposed some solutions where instead of predicting from left to right, you also predict from right to left, and use that information also during training. As simple as that, right? So that's very easy. So we'll discuss about this later. Just look at this. So as I said, you want to predict both left and right outputs. Let's say for the loss for the VAE, when you are predicting from left to right, you can use this equation where you are predicting a sequence of frames sequence of spectrogram frames from left to right from the corrupted version of the X, and same thing happens with the text also. You are predicting from left to right, the sequence of words from left to right. And LDAV from right to left is opposite. Like you want to predict from right to left given this sequence of frames, right? X, corrupted version of X, and you want to predict from right to left. So this is going from right to left, right? So this is a loss. And if you go to, this is the loss of DVAE, and now once you train this, you can go back to the dual transformation, and same thing happens here also. Like you have the dual transformation loss going from left to right is like this. So you have something like predicting x given the given the predicted version of y from ASR model, and you also have reverse sequence of it, and you also predict x given the reverse sequence. Same thing you do with text model, and you can use right to left model again, right to left loss again, and repeat the same thing. This is how the thing works. This is what the loss is. But people say will not just use this unsupervised algorithm. We'll also use some pair supervised data also. I mean, this is a unsupervised data. We have a lot of unsupervised data. We have, let's assume we take some very few amount of supervised data, and this is how the supervised data, because you're not predicting anything. You're directly using the ground truth x, and you're directly using the ground truth y. And if you add all these loss together, we'll see that final loss equation, and that loss equation will have the supervised loss, this unsupervised loss, and everything. Right? We'll see those equations in the coming slides. Finally, coming to the model architecture. I mean, I should have explained this architecture before, but I just wanted to give a heads up for all those new things. And finally, I'm explaining this model. This is how the model looks like. You have your this is the mod. This is like, I mean, if you know about transformer, I hope you guys know about transformer, because I don't have time to explain transformer. Transformer is like same encoder decoder architecture, but instead of using RNN or CNN anything, they use something called self attentions or multi-headed self attentions, and those are very interesting. These are, training is fast because you're not using an STM or CNN. So this is how the model is. So you have some encoder. It can be speech encoder or speech encoder or text encoder. You have decoder, which can be speech encoder or text decoder. Sorry. So in the DVAE training, what happens is you feed the speech and you directly predict the speech. So this model will be like this. So this green arrow will be there, right? This will be there. And in the same thing happens with VAE, because you are directly feeding the text and generating feeding the corrupted text and predicting the generated text. This is fine. Now DAV for speech is like you take the text. You take the text, and this red line says, okay, the predicted text will go to my speech decoder, and I get the speech. And this is TTS, because you are taking text and generating speech. And opposite of this, I mean, this is the part, and opposite of this is take the speech and predict text. Like, is the path is like this, right? And this is how the architecture works. So once you train, you have to first train your DVAEs, DAEs, which are denoising autoencoder. Then you can combine the models like this. So you can, if you want it for speech, you can use it as TSR, you can use it that way. If you want it for text to speech, you can use it this way. And this is the what is encoder, what is decoder, is all these things, because we are going with whatever the transformer based model, and don't worry about this much. So, and final loss will be like this. As I said, the final loss combines the left to right VAE loss, right to left VAE loss, left to right DT loss, right to left DT loss, left to right supervised, right to left supervised. So all these are jointly trained. And coming to the experiments, they are using something called LJ speech. This is one of the standard data set people use for text to speech, and it has 13,000 utterances. Out of which we use only 200 text speech pairs, randomly selected text speech pair for supervised, and remaining are all for unsupervised. And for the speech, they use millispectrograms with 50 millisecond window and 25 millisecond frame shift, and they use a transformer, as I said, and they train it on 4 NVIDIA P100 GPUs with batch size of 512, and which is the total sequence, and out of which 128 sequences for denoising autoencoder, 256 are for dual transformations, and 128 for the text speech pair text data they are using, which is the supervised data, right? And also they use, as I said, that's what as I told you, like what is in the batch size, how many sentences they are selecting for both transformations. I mean dual transformations and denoising autoencoder and supervised data. And coming to the evaluation, they are using MOS score for evaluating TTS, which is mean opinion score, and phoneme error rate for ASR, and also they measure something called intelligibility of voice, rate of intelligibility, which will give you like how intelligible the audio is and can you understand that audio. So that is the measurement they are using, and they are getting very high score there. We'll see those results. And for evaluating on tested, they sorry about that. So they take some 50 paired speech text for evaluating the intelligibility and MOS, and they if we give it to 20 testers, all are native English speakers. Coming to the results, so they have a ground truth which is having a very high mass score, which is because ground truth easily you can understand like what their people are speaking, and they also use it this as Griffin limb as some sort of upper bound model, because they are using Griffin limb for reconstruction from spectrogram to audio, and for that you get 3.21. This is sort of like taking the audio, converting it to spectrogram, converting back the spectrogram into audio. That's how it is. And if you use supervised, you get very high score, which is very good, because this supervised is using full data, full amount of LJ speech data, which is very good. And if you use it for ASR, you get 2.5 or PER, which is very less, very happy. But if you use pair 200 and you just train the TTS, you get nothing. I mean, the mass score is very almost zero. They're saying null, and PER is also worst. But if you use this pair 200 and unsupervised data, you get very good mass score, still good, 2.68, intelligible, and 11% is still okay. I mean, PR is still okay, right? Another experiment on ablation studies, like checking what if you use only this one, or if you use the 200 same supervised data plus DA VAE, the still if you use VAEs, it is not improving. I mean, the TTS out, I mean the mass is very low, but if you use dual transformation, it's giving 2.11. But if you use dual transformation with bidirectional sequence modeling, you will get 2.51, which is very good. And same thing happens with the PER also. And the second thing is they also have done some experiment with changing the amount of data, paired data. Like if you take 100 sentences, what happens to PER and also mass. And if you increase the amount of paired data, you will get a very good amount of or very good mass score and PER also, right? And thank you so much for watching this tutorial. If you are not subscribed to my channel, please subscribe. If you like this video, please give a thumbs up. Thank you.